In our introductory video, we looked at the big picture of this course. Today, we are officially diving into Lecture 1. First, we need to establish exactly what program synthesis is, where it came from, and how it differs from tools you already use every day. In this video, we will cover 4 main areas. First, the historical evolution of software automation, from Alan Turing's early visions to modern LLMs like Gihtub Copilot. Second, how program synthesis distinctively separates itself from compilation, declarative logic programming, and traditional machine learning. Third, we will establish a formal, concrete working definition for program synthesis. And finally, we'll look at real-world applications happening right now and break down the 3 fundamental pillars of modern synthesis challenges. Let's get started. The dream of making machines write code isn't new. It has been alive since the very dawn of computing. As early as 1945, while outlining his vision for the automatic computing engine, Alan Turing noted that constructing instruction tables would be a fascinating puzzle for mathematicians. But he also astutely pointed out that any processes that are quite mechanical may be turned over to the machine itself. Historically, we achieved this automation through high-level languages and compilers. In fact, when the very first Fortran compiler was released, it wasn't just called a translator. It was marketed as the Fortran Automatic Coding System. The goal was to let the IBM 704 code problems for itself and produce programs just as good as human coders, minus the human errors. Fast forward to 2021, and the development community got its first massive taste of modern automation with Gihtub Copilot. Suddenly, large language models were writing whole blocks of code. By 2022, DeepMind's AlphaCode was already competitive enough to outperform the median human coder in online programming competitions. But while LLMs have driven this explosive progress, they are only part of the story. Code demands absolute extreme precision. A single character can be the difference between a working program and a catastrophic security vulnerability. However, code also gives us a massive advantage. Unlike human text or images, code has precise semantics. We can test it and reason formally about exactly what it will do. To understand program synthesis, we have to contrast it with 3 closely related fields: compilers, logic programming, and machine learning. Both compilers and synthesizers want to generate software from a high-level description. However, a traditional compiler simply translates a program from one notation to another. A synthesizer is expected to do more. It must discover how to perform the task. Now, the line can be blurry. Aggressive optimizing compilers that handle auto-parallelization actually do discover how to parallelize sequential operations. Historically, compilers were deterministic while synthesizers relied heavily on explicit search. Today, even that boundary is fuzzy, as modern compilers use search for optimization, and LLMs can synthesize code without an explicit search step. Think of languages like Prolog. The dream of logic programming was that you would write down logical constraints, and the runtime system would deduce the output for any given input using a generic search algorithm. The difference? Logic programming relies on a generic, permanent engine at runtime, making it incredibly slow for complex tasks. If your problem is underspecified, it might give you a wildly incorrect answer. Program synthesis, on the other hand, tries to discover an algorithm to solve the problem. In machine learning, the canonical goal is finding a function that maps inputs to outputs based on a dataset. If you view those data points as input-output examples, ML looks a lot like program synthesis. But there are core differences. ML tightly restricts the function space to a specific architecture like a linear model, a decision tree, or a fixed neural network. Program synthesis aims to discover the underlying structure itself, including loops, conditional branches, and recursion. Because ML uses highly prescribed function spaces, it uses highly specialized, continuous optimization algorithms. Synthesis takes a broader, symbolic view. Historically, synthesis demanded programs that always perfectly match a specification. This has not been the case in machine learning, where the notions of learning from noisy data and using real valued measures of success has been deeply ingrained in the literature from the very start through the languages of probability, statistics, and optimization. While the synthesis community is becoming more robust to noise today, this philosophical difference remains fundamental. So, given all of that, how do we formally define the field? Here's our core working definition for this course. Program synthesis corresponds to a class of techniques that are able to generate a program from a collection of artifacts that establish semantic and syntactic requirements for the generated code. Let's unpack the two crucial elements of this definition. First, there is an emphasis on the generation of a program. We expect the system to output clean, deployable code that solves the problem, rather than forcing an expensive search engine to run every single time a user provides a new input. Second, it supports both semantic and syntactic requirements. We don't just want to control what the program does, we also want control over how it looks. We want to dictate what components it uses, how it's structured, or other non-functional constraints. While a specific tool might bake these constraints in behind the scenes, the underlying synthesis algorithms have incredible flexibility in defining the program space. This search space is exponentially large, and the true success of synthesis relies on our ability to navigate it without searching it exhaustively. Note that program here is broad. It includes code in Python or C, but also mathematical expressions and formal proofs. Today, tools like ChatGPT, Gemini, Gihtub Copilot, and coding agents like Claude Code have made natural language code generation feel ordinary. We've seen AlphaCode tackle competitive programming, and AlphaTensor discover matrix multiplication algorithms faster than any human had ever found. But amid all this AI hype, it's easy to assume traditional search-based synthesis techniques are obsolete. In reality, they are more relevant than ever. LLMs have massive weaknesses. They provide weak to non-existent correctness guarantees, consume immense compute and energy, and struggle to adapt to custom, domain-specific languages without massive training data. Before the arrival of LLMs, the field of program synthesis focused on a different method: efficient search techniques. These systems would look through huge spaces of possible programs to find the exact one that met a set of requirements. These early techniques did have limits. They could only build fairly small programs, and they could not understand natural language. Even with those limits, they achieved some amazing results. For example, they were able to synthesize complex algorithms like Karatsuba, big integer multiplication, Strawson's matrix multiplication, and the famous Cartesian product algorithm by Baran and Strachey. These search-based tools were also incredibly good at low-level math logic, like bit vector operations. In fact, in a 2019 program synthesis competition, the winning system successfully solved every single bit vector problem the organizers could think of. Search-based techniques were also designed to work well with verification, enabling the synthesis of provably correct implementations of fairly complex algorithms. Within a few years, the field moved from solving simple tasks like sorting lists to automatically building complex code for data structures like inserting items into binary heaps or red-black trees. In stark contrast to LLMs, which are trained on large amounts of data and require significant compute resources to run, search-based techniques can be engineered to be extremely efficient and effective as long as they are tailored to a specific domain. Most importantly, as we will explore later in this course, these exact symbolic and search-based techniques are now being used to improve the performance of LLMs and to make them more reliable and easier to use even outside of the context of generating programs. Where is this applied in the real world? Let's look at three massive domains. Long before modern chat interfaces, Microsoft introduced Flash Fill in Excel 2013. It was the first mass-market commercial application of program synthesis. By giving Excel just a couple of examples of how you want data formatted, a synthesis engine automatically infers a small program behind the scenes and applies it to thousands of rows. This sparked a wave of research into synthesizing database queries from simple examples or natural language. Instead of going from a specification to code, what if we flip it? Verified lifting takes an existing, messy, or legacy implementation and infers a clean, high-level formal specification. This allows engineers to automatically translate old legacy code into highly efficient, modernized versions, like turning old imperative loops into clean, optimized SQL queries or hardware-accelerated tensor computations. The application of synthesis to reverse engineering is not limited to reverse engineering programs. Back in 2013, a group of researchers demonstrated the use of synthesis for inferring models of regulatory networks from experimental data. They decided to treat this biological system like a hidden computer program, and they treated the data from real-world lab experiments as the program's inputs and outputs. Their goal was to use a synthesizer to automatically write a program that perfectly matched the data from the experiments. Today, this same approach is used in many other fields. For example, linguists use it to discover the hidden grammar rules of human languages. In general science, this approach is known as symbolic regression. Instead of just drawing a random line on a graph, symbolic regression looks at scientific data and finds the actual readable mathematical formula that explains it. The advent of LLMs has enhanced the model building process, allowing it to scale to larger and more complex models, as demonstrated by the World Coder system. As we wrap up our introductory lecture, it's clear that whether we are using modern large language models or classic mathematically precise symbolic search, program synthesis is fundamentally changing how we interact with code, science, and engineering. But behind every successful synthesis tool is a core foundational question. How can a machine safely guess the exact code a human wants based on incomplete information? That brings us directly to what we are covering in Lecture 2, Introduction to Inductive Synthesis. Make sure you hit that subscribe button so you don't miss the next deep dive. Give this video a like if it helped clarify the boundaries of the field, and I will see you all in Lecture 2.